All right, 3.1, Introduction to Mathematical Reasoning. So to kind of just establish some background like rules that we'll use inside of proofs to start off, and then we'll have a whole series of rules beyond that, is that we have even and odd integers, proofs, conjectures, counterexamples, divisibility, and prime numbers. So definition of an even and odd is that when we look at this idea of wanting to use arbitrary numbers, I mean, we obviously know that even numbers are things like 2, 4, 6, 8, etc. And so what we're saying is that n could be, if an integer n is even, provided there's some integer k where n is equal to 2 times k. So if you plug in 1 for k, 2 times 1 is 2. If you plug in 2 for k, 2 times 2 is 4. If you plug in 3 for k, 2 times 3 is 6. Plug in 4 for k, 2 times 4 is k. So you always get an even number with this analogy. So that makes it an arbitrary. So it's not like we're like looking at one specific even number. We're looking at arbitrary even numbers. And we can use that to prove things inside of our proofs. And that just makes it more of a solid proof of something. And then we have the same idea with odd integers. And so that if we know that odd numbers are 1, 3, 5, 7, etc. And so in that case there, we say, let's say k is 1. So 1 times 2 is 2, plus 1 is 3. Let's say we let k be equal to 0. So 0 times 2 is 0, plus 1 is 1. Let's say we let k be equal to 2. 2 times 2 is 4, plus 1 is 5, and so forth and so on. And so we break down this definition, we can also see that, it's some factor of, and so you can kind of look at it two different ways. So even and odd integers. All right, so our first proof then, don't know why I'm getting lag here, sorry about that. Our first proof is we want to prove that if an x and a y are even integers, then x plus y is even. And so to do this, we're going to kind of like think about this preparation. Like this is kind of getting us like to kind of process the information and be able to say to ourselves, what do we need to like think about in order to make this work? And that's just going to help the process of actually writing the proof. And you'll see that most of the time, the preparation is actually a longer drawn out thought process. And, this is very formally written out, but please make sure that you consider just like jotting down your ideas before jumping into the proof. Like, what are the definitions? What are the rules? What are previous theorems you might have come across, and so forth. So let's kind of talk through it. As we've seen, it is not enough to look at specific examples to prove that the theorem is true. We must find a way to discuss all of the even integers at one time. So that's that arbitrary thing. So instead of looking at like 2 and 4 and saying, okay, like in this case situation, we could say 2, let's say x is equal to 2 and y is equal to 4. So then therefore we can say those are even integers. So then that implies that 2 plus 4 is equal to 6, which is even. And that's like, check, we're done. Therefore, kind of done. Well, that doesn't work that way because that's just one specific example. Just like we'll get to counterexamples later, you need to look at all possible situations to be able to prove something true. So by using an arbitrary scenario with the variables, then we accomplish that. So to accomplish this, we want to represent x by 2k and y by 2j. And so that is just saying that no matter what we plug in using that definition, then we know that we're going to get an even number for both. So since we did not specify k and j, any result we obtain from the discussion of 2k will be true integers for all, will be true for all integers. Not sure why that's not changing the page. There we go. All right. So here's our proof. So the proof is up here. Down here, this is just kind of like some talking our way through it, kind of making sure we understand what we just did. So we start off with this idea of like if P then Q. So if x is even, then there's a k such that x is equal to 2k. So that's straight from the definition of an even integer. And since y is even, there is an integer j such that y equals 2k. So let's think about that as like the rule of detachment. So that's like these are our premises that we're establishing up here. So those like kind of establishing the premises of what's going on here, the ifs. So if we have this, then kind of thing. And so we get to this spot. So we've established the if part up here. Now we're trying to get to this x plus y. So then we go into the x plus y. And so we say x plus y is equal to 2k. So we're just using like our algebraic rules. We're substituting things in. And then this is just kind of one of those things with familiarity. Like we pull that out front. So at that point, when we pull that common factor of 2 out front, what happens is we've basically said that by definition, whatever we have here is going to be an integer. And so an even integer, excuse me. And so therefore we can say since j and k is an integer and x plus y is 2 times an integer, hence x plus y is even. It's because of this little statement right here that we're seeing. So that's kind of like, getting ourselves familiar with this whole process of like plugging things in and what it's going to look like. It's going to take time by just looking at examples. And that's what I just want to encourage you to do. Our proofs are very dependent on patterns of valid reasoning discussed in chapter 1. As you read through proof 1, did you think it in this way? And so I kind of like already pulled that out, and that's the rule of detachment. So if a equals 2b, then b is an integer, and a is an even integer, and so therefore we get this actual statement coming out. And that's that fallen idea of if p, then q, if p, then therefore q. And so that's kind of what we're doing here in this first kind of set. And so we'll be looking at different ways we can prove theorems. Most of the time, I'll be guiding you. I'll tell you, do this proof by rule of detachment. Do this proof by direct proof. Do this proof by, and so it'll always kind of be telling you what to do. So a couple of things to kind of just note. These are like the things, like nothing, there's no need to write this down. This is just like hearing it and kind of like reading it as I'm saying it to you is like all that really needs to be done at this point. These are just kind of like things to kind of keep in your mind. At this point, we need to reflect on 2 explanations that we have just completed. When after observing a pattern for several examples, we formulate a statement to describe our observations, this statement is called a conjecture. So looking at several examples of patterns, we kind of have this ability to kind of get a conjecture. That's like the if part. That's like your educated guess. When investigating conjectures as possible potential theorems, we are always attentive to examples for which the conjecture does not work. An example for which the conjecture fails to hold is called a counterexample. The great thing about a counterexample is the existence of one counterexample proves the conjecture false. So it's really easy to prove something false. It's really hard to prove something true. And so that's why we have to look at arbitrary scenarios, because we got to look at kind of like it works for any scenario versus just like a few specific. Whereas with a counterexample, you can prove it false for one thing and you've proved yourself what you needed. Proofs of theorems depend very much on definitions of the objects being discussed. It's good to practice to review all relevant definitions carefully before attempting a proof. And that's what that like prep is that you're doing. That's this piece right here, this preparation for your theorems. So that's like making sure you kind of like thinking about like, what are the rules? What are the definitions? What might I do? What have I seen in other examples? How could I apply that here? What's the format? And so forth. The proofs we write are seldom complete, but are rather only outlines of the complete argument. Typically, proofs are very dependent on knowledge gained from previously proved theorems, often theorems learned in our mathematics education. For instance, in the proof of theorem 1, we used the fact that k and j are integers, then k plus j is an integer. That fact was learned in earlier courses. And that's just like, there's like so many rules out there. So just like what we're doing is to kind of hand them to you as we go. So they'll kind of be in the sections and so forth. So everything should kind of just tie together and become familiar, since it's just a introductory discrete math class. We can freely use properties of operations on integers, natural numbers, and real numbers. So we can use like any of the properties, addition properties, subtraction properties, any like the subset properties and so forth. We also can use elementary algebra that results from those properties, like factoring, manipulation of algebraic expressions, and so forth. And so just kind of like stuff to keep in mind as we move forward. All right, so that finishes up section 3.1. Please reach out if you have any questions.